we were talking that what is the significance of the existing solute in the medium. So it depends upon its concentrations in aqueous phase, or it depends upon the concentration in the solid phase. We also talked in the previous lectures that these two phases are actually in equilibrium with both of with each other. So for example, if a solute is entering into the soil medium, it will be firstly existing in the pores, and then based on its particular characteristic, it can get attached to the solid phase, or it will get dissolved in the aqueous phase. In both cases, it will be having an equilibrium with its the concentration which initially entered into the solution entered into the soil volume. Therefore, we are more concerned with the equilibrium. So that equilibrium must be maintained between these two phases. These two phases are aqueous as well as solid. In the solid phase, the texture which the solid particle of soil is more important, because this is going to define whether the solute is going to get adsorbed, or it is going to be existing in the aqueous phase. And so this is the actual phenomena of the sorption and desorption. We will talk about it in detail, but just for an initial introduction to this concept, we are concerned with the amount. That amount must be in equilibrium. So this is how we will quantify the contaminant or solute, and this is how we will trace it in different locations. So if it has if at the initial stage, at the boundary conditions where the solute is entering, we are having a typical quantity of a solute. For example, we talk about chromium and it has a concentration of 10 milligrams per liter. This amount is entering into the soil. Now in the soil, it is going to be existing in aqueous phase or in the solid phase. So it will giving us different concentrations for different times as well as for different locations. We need to have a breakthrough curve for the concentration versus time variation. So at a particular location, how the concentration is changing uh, with respect to time at a particular location, and how this concentration is existing in equilibrium. So firstly it will be found in aqueous phase, then it is getting attached to the solid phase. So we need to have an equilibrium between the concentrations. So the ratio between the amount in the aqueous and in the solute must be balanced. So let's talk about it in detail. So desorption refers to a mass transfer process between a contaminant dissolved in groundwater liquid phase and the contaminant sorbed on the porous medium solid phase. Therefore, it is also known as partitioning. So partitioning is between their the shift of the contaminant between these two phases. Initially, it will be in the aqueous phase, then it will be moved to the um, solid phase. So this is called partitioning. So we need to focus on the equilibrium, their equilibrium, and this equilibrium is actually going to lead to give us a detailed analysis how the contaminant is traveling. Our most of the equations, continuity equations, are all based on this. So this is the process of sorption, in which we will be talking about the liquid phase and the solid phase. So it is all about the transfer mass flux between the aqueous to the solid. So sorption encompasses various processes, how it can take place. So mass transfer is normally existing is conducted by uh, absorption, adsorption, and ion exchange. So adsorption refers to a contaminant clinging to a solid surface. So absorption refers to the contaminant diffusing into interior of solid and being adsorbed into the interior surface. So if you see here on in this picture, you can easily observe that this A, which is a solute, when it is coming in contact with the solid phase, it is going to get attached with this solid phase in the case of adsorption. While in the case of absorption, our solute is getting absorbed, completely entering into the surface of that medium. So it has become a part of that solute, that solid phase. While in case of ion exchange, normally we are going to have a shift between the ions. So ions will be partitioned, will be separated, and they will move to the respective uh, electrodes. This is the mechanism for ion exchange, quite familiar. So this is now another description how how our water is moving and how it is carrying the contaminant. So first of all, through the pores, and then we have a path length, it is for longer durations. Then we have a friction in pores. So all these things are the different scenarios which are considered while talking about the movement of contaminant. The mixing that occurs along the direction of the flow path is called longitudinal dispersion. So when we talk along the length, along the movement, so if the contaminant is getting mixed in a particular direction, it will be called longitudinal dispersion. So it is the mixing of solute. It can be mixing uh, from the solid particle which is desorbed, and now it is getting back to the aqueous phase. This is also one of the modes which will take place, but usually what happens that the contaminant is moving from the liquid phase to the solid phase in the case of sorption. And what is the reverse? Desorption. And in the case of desorption, the solid particle will get detached from the solid phase, and then it will be entering back into the liquid phase. This is the desorption process. And that in direction normal to the flow path is called transverse or lateral dispersion, in which the geological formation is again important. The local scenarios of the interlocking of the grains or the geological formation is also important. The available path for the movement is also important, and then the velocity with which the water will be flowing through these pores is also important to describe this phenomena of dispersion. So factors causing longitudinal dispersion at the scale of individual pores and flow paths in a porous medium that causes lateral dispersion. So there are some conditions using which we can develop an equilibrium. So for developing equilibrium, we must have uh, mm, some continuity in a characteristic. So considering the temperature to be same, and considering a sorption process in isothermic conditions, we usually have isotherms to describe our scenarios, and those scenarios are based on our assumptions, whether it is about the geological formation, whether it is about the grain size, or whether it is about the concentrations. So anything which is changing is developing a different scenario. So we are having different sorption isotherms, with the help of which we will be developing a relationship between the concentration of the solute in the aqueous phase and the concentration of solute in the solid phase both. So a relationship between the equilibrium concentration of solute and that sorbed by the unit mass under a constant temperature is referred as the sorption isotherm. So this, in this case, we are considering that the temperature is considered as constant. So our physical properties are considered as constant. So we are not changing our density of water or density of the medium or humidity or moisture content. Any such thing is not being considered to be changed because we are considering a constant temperature. So under these conditions we will be developing equations for the equilibrium. So first of all, starting with the linear isotherm, this is the most simplest assumption and scenario development, in which uh, the soil has an infinite sorption capacity. As much as the flow is coming of solute, it will be having getting adsorbed in the medium. So mathematically, the linear isotherm is expressed in this form. So C solid is equal to Kd, which is the partition coefficient, and multiplied by the C equilibrium. So this C equilibrium is actually representing the amount which will be existing in the aqueous phase concentration. Sorry. So RD is represented by, in this form, is equal to, it is retarding factor, and retardation can be in the form of some frictional forces or some other chemical reactions which are taking place, and rho b is the dry bulk density. So Friedrich isotherm is again following the same assumption that there is no limit to the amount of contaminant that can be sorbed on the soil grain. And again, in this case, we are having this equation with a different constant values, and these constant values are based on the our introduction of new parameters. So those parameters which were not involved in our linear relationship is now involved in the Friedrich relationship, and these are rho b is included, n is included, and so these are actually developing the much more uh, uh, explanation to our relationship between the aqueous and solid phase. So these are the relationship graphs here. And then we are having a Langmuir isotherm, which has been developed on the concept that the solid surface processes a finite number of sorption sites. Now we are going to limitize, and this in this case we are again having different constants, like A is the adsorption constant related to the binding energy, B is the maximum amount of contaminant that can be adsorbed by the unit mass of solid. Now these are included because we are considering, because we have a finite number of sorption sites on the solid phase. So that's why we are limitizing our expression through different constants. So A and B are introduced. Similarly, we are introducing the relationship between C equilibrium over C solid, and this ratio will be expressed versus the C equilibrium. So again, this is to limitize our amount which is going to get attached. So now the development of the advective dispersive equation, which is also called a convection dispersion equation. We have talked so much about it. Most widely used approach to describe solute transport in porous medium. So derived by imposing the conservation of mass upon transport, which includes convection, diffusion, and dispersion, scale dependent dispersion, and there are some very useful analytical solutions to ADE for special cases, which give insight into many real world problems. For derivation, we need to consider a scenario, and we need to consider a system, and that system is normally represented by representative elementary volume REV to obtain a solute mass conservation equation. So conservation equation we earlier talked about, that the coming influx is equal to the outflux, input is equal to output, and plus the changes which are taking place within that volume. So look at the flux term at the microscopic and macroscopic level to identify transport processes which are added to the solute conservation equation. So furthermore, we add chemical reactions, decay processes. This is the equation development. If you find, and it is based on this balance. So this is more important for us to understand. So anything coming inside is equal to the outside, as well as the processes which are taking place inside this box. So here you can see rate of solute mass increase within the volume is equal to the solute mass flux into minus solute mass flux out, plus increase or decrease of solute mass due to various reactions. So the rate is equal to this much amount. So I think it's quite understandable, and the derivation is based on the conservation of mass, which we talked about, and based on this we will be having very typical phenomena. One type of chemical reaction which increases the mass contaminate in the REV is sorption. uh, so how it can you explain this? Because the sorption is the process, is actually the chemical or physical process through which the solute is getting attached to the solid particle, or it is getting absorbed with the solute, with the solid particle, or it is having an ion exchange. So all these are actually the chemical reactions taking place, which will be representing our sorption and desorption processes. So this is the key function of any kind of contamination in a typical environment. If we need to understand the behavior of solute within a soil mass, we must understand the sorption and desorption processes which are taking place within that volume of soil. So based on that we will be developing this equation, and then we can quantify the concentration and its variations, and we can determine the fate of contaminant within our predefined boundary conditions. So we will not go into the detail of this whole equation development or its derivations. It will be very lengthy process, and actually it is all continuity equations, and it will be involving some matrices and their solutions. So quite a complicated process. It is more important for us to understand what are the basic principles, how this contamination transport is actually taking place, what are the phenomena involved, and how we can study this process when we are actually assessing a contaminated site. A Piglet number is now a very important uh, uh, parameter to differentiate between the sorption process and desorption process. Now how we will define it? We will actually develop a relationship between the advection process and the and the diffusion process. So what was the advection process? It is the change in mass transfer through the flow, through the velocity, and through the advection process. and it is involving the velocity of the Darcy velocity through which the water is moving. And it will again define the process, the behavior, and then the second is the diffusion, in which we will be having concentration gradient with respect to distance from one place to the other, which is according to the Fick's first law. And what was the Fick's second law? It was about the double derivative with respect to time as well. So it's all about the mass transfer from one place to the other, from one phase to the other, and that phase is actually the liquid phase to the solid phase, and this shift is actually going to be describing our sorption behavior. So once the contaminant in this solid soil aqueous phase is determined, and at some other place, if it is not found in aqueous phase, where it has gone, definitely it has been attached to the solid particle, and the other option is that it has passed that section, it is no more there. So two processes are involved: advection process and the attachment process, that is the sorption process. So advection and sorption both are taking place simultaneously. So we are going to have a relationship, we are going to find the ratio between both of them, and in that case we will be determining whether this which one is dominating. So advection is dominating or the sorption is dominating, and based on this we will be actually defining the sorption and desorption processes, and we will be defining the partitioning. As I talked earlier, partitioning is another factor which is important to differentiate the behavior. So that partitioning is actually represented through this Piglet number. So a typical Piglet number will define which is dominating now, which process is dominating in this particular condition. That's why this Piglet number is going to define the partitioning between these phases, liquid phase as well as the solid phase. And what is the importance? Again, we will be able to determine the equilibrium. So we need to understand where the contaminant is existing, whether in water or in the solid. Here is the expression. If you see PEL is equal to VS into L, the upper part is the uh, um, advection process, and the DH is the uh, diffusion process, and the ratio between both is going to give us the Piglet number. A relatively high Piglet number greater than or equal to 50, advection dominate transport process will be taking place, and if less than 1, it will be in diffusion process which will be dominating. So Piglet number PE is a class of dimensionless number relevant in the study of transport phenomena in a continuum. It is named after the researcher scientist. It is defined by to be the ratio of the rate of advection of a physical quantity by the flow to the rate of diffusion of the same quantity driven by an appropriate gradient. This is the relationship. PE is equal to advective transport rate over diffusive transport rate. So L is the characteristic length, U is the local flow velocity, D is the diffusion coefficient. The simplest relationship which you can understand easily. And then there are some of the ranges. So for zone 1, 2, 3, if PE is higher than 0 and less than 0.4, diffusion dominates, and if higher than zero point 0.4 and less than 5, then mixed dispersion and over diffusion is possible. And if it is less than 10 and greater than 5, it will be having dominant longitudinal and combined effects in transverse. So similarly, PE greater than 10 and RE is the Reynolds number. Less than 1, dispersion dominates and linear non-inertial flow will be taking place. So Reynolds number is also an important factor which defines whether the flow is linear or non-linear, turbulent or steady. So both are equally important. Normally in our equations we consider steady flow, because if we consider non-steady or turbulent flow, it is very difficult to develop the 3D equations in case of that turbulent flow. So keeping the simple flow, keeping the steady flow, make the calculations and mathematical expressions much easier to be developed. So that's why it is preferred to consider a steady flow rather than considering a turbulent flow. So these are the typical values. I think you can go through them by yourself. And now something about the decay process. Naturally, when there is a chemical reaction taking place, the in the the solute which has entered into a typical medium, it will definitely react, and it will change its formation and its nature. So as a result of that, the original behavior of that contaminant will be totally changed. So it will be now a different radical or ionic bond which will be existing, and that as a result of that the effect will totally change. For example, chromium in fresh waters is like hexavalent chromium. With the passage of time, this hexavalent chromium gets reduced to trivalent chromium. And this trivalent chromium has more affinity to get attached to the solid particle, that's clay. And because of this attachment, now the trivalent chromium is more easily available in the solid particle rather than in the aqueous phase. In the aqueous phase we will be having hexavalent chromium, and in the solid phase we will be having trivalent chromium, because with the passage of time that hexavalent chromium would reduce to trivalent chromium, and it will get attached to the solid particle, and as a result of that it is going to have much more retention. So if in our soil we are having trivalent chromium, that means it is indicating a chronic source of contamination, not fresh introduction of the contamination through chromium. And if our waters and our monitoring wells are showing hexavalent chromium in excess, it means it is indicating fresh intrusion of the contamination from some source like wastewater coming from tanneries or something like that, which are having their effect, and it is very recently introduced into the medium, so it is existing as a hexavalent chromium. So we will be evaluating both hexavalent as well as the trivalent chromium, so that we can understand that whether the contamination is fresh, acute, or it is a chronic contamination. So again it is based on the equilibrium between the aqueous or the solid phase, and based on that we will be easily understanding the source from where it is coming. So similarly it is quite a long discussion to be continued. Today we will stop it here. And next, in our next lecture, we will be talking about the behavior, just like we talked about chromium, how it is going to behave. And so we will be understanding how this shift is going to take place and how it is going to help us in assessing the contaminated site, and then how it will be helping in developing some solution to this. So naturally we will be, after our this behavior discussion, we will be moving forward to the other sources like landfills, and then how landfills are actually contaminating our soil environment and groundwater environment, how we can stop that. And then we will move to the some remedial approaches, how hexavalent chromium is to be dealt with, and how trivalent chromium is to be dealt with. So we have to adopt different approaches for both kind of contaminations. Thank you very much.